Hello, and welcome to another video. In the past, I've covered pressure engines, but I'm going to cover them again now, just so that everybody can know what's up. You may have seen on YouTube or Reddit or Discord, there are these types of piston engines in scrap mechanic called pressure engines, and you may have no idea what they are. Well, they're a type of piston engine that takes advantage of an effect I call the pressure effect. And they make incredible amounts of horsepower. They're really handy for things like race cars. But they're a bit tricky to build. They're not like most piston engines. So, if you've played scrap mechanic for any length of time, you're already familiar with a piston. You power it, it extends. You unpower it, it retracts. You can change the distance it goes to, the speed it will try to go to the distance with. You'll also be aware of the bound forces. So say for a bearing, it's pretty easy to make this bearing rotate, but it's rather difficult to try and stretch it away from its joint, unless you have something that can produce an incredibly strong force like a lift. Piston is the same way. It's rather easy to move it along this axis, but it's rather difficult to move it in any other direction, including compressing the piston like back into itself. So, going back to the speed characteristic that the piston has, you can say, for example, connect it to a controller. And, this will make it go really slow. You change the time on the controller, it goes faster. You change the time again, it goes faster still. Well, with a blueprint editor, what we can do is we can click on the controller and we see the JSON information of it displayed. We see the time per frame. This is essentially the time value, how long the piston is trying to take to get to its destination. So we can type in a smaller number, click apply, and it goes a little faster. We can type in a smaller number, and you'll see it goes quite a bit faster. Now, this a piston will restrict its speed. Like if you force it to go some speed, it will apply a dampening force if it exceeds the speed it's allowed to go, which would be in the controller or its default settings. This also applies to the bound force. So if the child object of the piston were to say be compressed backwards, if you were to like put pressure up against the piston to like push it back, you would now be running into the retaining force, the like primary retaining force of the joint, but you would no longer have this dampening effect. Or at least this dampening effect would only kick in once it exceeds some speed. And if you give it a target speed that is essentially infinite, then that dampening effect will never kick in. So then what you can do is give the piston a lot of momentum, or a lot of inertia, and it will start to bounce back and forth. Let me really get it going. Yeah. Now when it hits the end of its travel and the back of its travel, it wants to use that bound force. So instead of the normal just pushing force or pulling force the piston has, now it has the much stronger retaining force pushing it. And that much stronger retaining force is going to kick the object really hard, and it's not going to slow down because we've essentially removed its target speed dampening. And this is the basic principle. You put a lot of force or pressure, you try to compress a piston, and you have this retaining force, and this retaining force will kick the object back. So that's the basic principle. Now, we can do that with a reciprocating motion. We can have our crankshaft, we can have the conrod, and our piston. And this is the most basic example of a pressure engine. Now, since you don't need timing, and since they rely on their position, they tend to snap to a specific RPM where they're happy. And there's a method and a science behind this called sync speeds, and it goes into the difference between real degrees per tick and indicated degrees per tick, but that's outside the scope of this. I can connect, say, a power source to the crankshaft, and I can give it a kick, and then I don't need it anymore. Once it's running, it'll lock into this RPM. And we can see that the piston is compressing within itself, and that rebound, it's putting that kinetic energy back into the flywheel. And this is really powerful. You can tap off a lot of energy from this. This is the most basic example. If you want to move up a notch, you may have seen Andrew's Kind engines. I've worked with him on some of the newer pressure engines and these old ones way back in the day. And a lot of Kind's engines, they use essentially a dual Scotch yoke configuration. So you'd have two Scotch yoke engines at 90 degrees to one another. And that's the Kind engine everybody knows and loves. Now what you can do is you can try to take this pressure effect and you can add it to that layout. This is a simplified version where we have a slider that allows the parent, or as I guess the child object of the piston, to slide freely back and forth, while the end of it that's getting the force is free to move up and down. So these two combine and you can complete a circular motion here. So this would be a essentially a Scotch yoke engine or a half Kind engine, pressure engine. And it does the same thing. It locks into a specific RPM and it stays there. And you can load the engine. You can do this with this one as well. I can have a turned off gas engine and I can apply some amount of load to it. You know, this would be producing a braking force. And it'll remain locked in at that RPM until you exceed the power output. What is it? Now I'll show you a better version of this. This prototype is pretty crummy. I just pulled it out to show you the logical progression of this. Now keep that in mind, all right? Keep that in mind. Keep everything I mentioned in mind. I'm going to go on a little tangent here, but I promise it's related. You've probably seen bearings on some creations that are tilted like this. And you may see this and you go, well, what on earth is this? This is what we call a wonk joint. A block will have a set of orientations. Now, what we can do, the bearing has a much larger set of orientations. We can go in and we can modify these. So we can essentially squeeze and stretch and distort the bearing, which direction it wants to face and thinks it's facing, so that it stops behaving normally. But this would allow this to essentially be these retaining forces are gone, or at least conditional. So this is the child of this bearing, and it's now pretty much free to move along this plane and rotate. We can do the same thing for a piston. So we can wonkify this piston, change its rotations, and now it is condemned to this plane. Give it a less aggressive nudge. Okay. You'll see what I'm talking about anyway. So you see it over there, right? See it over there? Well, I can still tell this to extend and contract. And that's really handy. So we can have a child object of a piston that is free to move along a plane, but is still bound vertically by the piston. And we can essentially do that here. We can take the piston that's providing the power, and we can use the freedom to translate along a plane as the one axis of the reciprocating motion, and we can use the extension of the piston to make up the vertical component. So we can now complete a powered rotation with only one piston. And this is the principle, that you can still put a lot of momentum on this, push against it, and that will still rebound, but it's, you know, free to move about in this way. Hold on to that as well. Another thing we do is with the blueprint editor, you have these axes here. We can go ahead and modify the axes to make this have zero width, or a zero width block. So bear with me here when I show you this. So this is made of a lot of zero width blocks. We can see here we have a wonk piston. We have a wonk piston here. I know it doesn't look like it, but it is. And we have these pipes here. So I'm going to go ahead and color this so it's a bit easier to see what's going on. So we have the parent object that the pistons are placed off of. This would be the majority of what's black here. The child of the piston, so what is placed on the piston, are these pipes. So it would be essentially if I did this and I wonkified this piston. So it's free along this plane. So that green pipe, these green pipes, they're free to move up and down, but they're bound by the extension and contraction of the piston. So this would be so far like this, but flipped around. Anyway, imagine a boxer version of this. Now, again, if we put enough momentum into this flywheel here, which would be the concrete, and this red zeroth block, which is sharing the bearing in the middle here, then we can start the engine. So now it's running. We've got it locked into its RPM, and we can go ahead and put load on the output shafts of the engine. So this is, I know this is pretty complicated, but everything here has a rhyme and a reason and an exact science behind it. So far you might be thinking, well, what are the applications of a pressure engine? Why might I want them? They seem, locking into a specific RPM doesn't seem very handy. Well, that is true. Locking into a specific RPM can be a little bit difficult for some use cases, but the benefit of a pressure engine is they can make like thousands of horsepower, which is really good for a lot of race cars. This one, we can see here, pretty much the same deal. We have a zeroth block, again, normal block. The piston is placed on it. It's a wonk joint. The child of it is a pipe that's connected to a flywheel. As the flywheel spins, it's taking advantage of the extension and contraction of the piston. The momentum of the pipe through the flywheel compresses the piston, and the piston, without its dampening, rebounds. And that rebound kicks the pipe and thus the flywheel back around. Okay, now, with all that in mind, I'm going to build a really simple, just a rather simple modern pressure engine. So we need to have the two opposing pistons. So what I'm going to start off with is a bit of a frame. One property I should mention is that when you wonkify a joint, again, how I mentioned these retaining forces, the retaining forces will change depending on whether the center of mass of what you're working with, is inline or centered around the piston. So you have these two opposing pistons that are placed on a zeroth block. We're also going to need something for the flywheel to be built off of. So let's go ahead and start this. Now, here we're going to need the flywheel. Most people like to use square mesh. I like to use the solid net, so I'm going to use the solid net because I'm different. If you're a civilized person, you just use the bounds control, but I'm really old, so I don't do that. Now, this is important. When you when you make a block a zero width, it needs to have some amount of mass on it. Because for all intents and purposes, they don't have mass. Built into the SMTC tool pack is a safety feature that will delete any zeroth blocks that don't have any mass, because they can go fly off into the void and mess with the integer limit, and your game won't be very happy with that. So what I'm going to do here, I'm going to place a part. if you want to be really easy about it, you can work with parts, but you don't want to end up subdividing the block you're working with. So now these are still connected, but they haven't updated. So I'm going to keep moving this into position. And yeah, just move this around, whatever. So now they're connected. So then I can go ahead and place down the bearings that will be on the flywheel. These will go here. And you should really paint as you go, but I'm really not in the mood for that. Right, I'll show you my car in a minute. So if I have any glitch welded concrete, it's probably more than enough. So now these are sharing a face. So the concrete is sharing a face with the parent object, which would be the flywheel, or the child object. So now we can remove the thing we had here. So I know this might look pretty wild, but just to recap, we have two zeroth blocks that the pistons are placed off of, a normal one in the middle, which we can make zeroth later, a zeroth block acting as the flywheel, and concrete giving the flywheel its mass. And you can make a kind pressure engine, or a Scotch yoke pressure engine, fuzz kind pressure engine, whatever you want to call it. You can make these without zeroth blocks, but it's really difficult. And they generally stink. The zeroth blocks give the pistons the clearance they need in order to have, well, in order for the chod pipe to be flying around along the length of it. So right now, if I were to wonkify these pistons, they wouldn't necessarily want to play nice, because the center of mass of the parent is way over here. So what we need to do, I might actually trim this down a little bit because we need to make this symmetrical. So on the y-axis, I'm going to move this in. We can get rid of that. We can move these along. So our parent object, again, we don't want the parent object to have no mass. We can go ahead and place, I'll use a really heavy part as a placeholder. This guy. I'm going to do again. So, okay. I built, I built a flywheel off of this pipe and that bearing. But because that's there, I would need to mirror this on the other side. So what instead I'm going to do is I'm going to make the flywheel the parent of the bearing that's supporting it to the crankshaft. Okay, so I colored it so you can see what's kind of where the different bodies are. So I'm going to place a bearing here, and keep in mind this bearing is placed on this pipe. I'm going to place another block here. I'm going to weld it here. And going to make it Z-width on this axis, and I'll just paint it to match. Yeah. So we have this, and now this middle Z-width block is sharing a face with these two adjacent ones. I'm going to go ahead and show you a couple other things. So how do we actually get shaft output power out of this? What we'll need to do is, again, I'm going to build this like I'm an old man. You can move this into place. Get rid of this. Now, you may be a little confused. What's going on here? Well, zeroth blocks have some conditions on what things are connected to what sides that will either enable or disable collision between them and things. So that, I'll just spare the gory details. The conditions here, you want the edges of your zeroth block to be sharing a face or meet the dimensions of a full cube on the negative directions of each of these. Just a general rule of thumb. There's some other things to it, but that's what's allowing this pipe to spin freely and not freak out. This pipe is connected to this pipe and this one subsequently. In between these two it's sharing a face with this red what is it, square mesh I like to use, solid net. So now one other thing, what we need to do, and I'll build it like I'm an old man, giving the body some inertia, ignore the land ship in the background. And we can trim this. And this is all fine and dandy. What we can do then is, again, the center of mass of this needs to be more or less preserved. So I'm going to use a joint, bearing, piston, whatever you want. And I'm just going to make a little platform. So we have this here now. And if I were to power this, nothing really would happen. That's because these pistons are not wonkified yet. The child green pipe isn't free to move up and down on this axis. So you can go over, remove this. Wonkified joint, apply. Over here, wonkified joint, apply. And now it may not look like it, but it is. You want to keep track of that. The pistons will usually do either an itty-bitty change, or they'll look like they're rotated or skewed in some way. So now we need the controller. We can go ahead and set the time per frame to 0, or just some arbitrary small number. Give your input power source, and there you go. There's your pressure engine. So this is a really rather simple one. If you want to get more power out of these engines, you can stack the bearings that make up the what we call the connecting pins or connecting pegs. Since with a reciprocating engine, you'd have a con rod, but we don't really have a con rod. We just have a single thing here. You can make that heavier. You can stack the bearings. You can also make the flywheel heavier. Now, those will all increase the power output of the engine, but they will start to plateau around 4,000 to 5,000 horsepower. Now, because of the mass rule property of low physics, you can go to physics 8 or any other lower physics level, and the increase in mass of the components will directly scale with the increase in power output of the engine. So if you put like 40,000 tons on the connecting pegs and flywheel, you can get like 40,000 million horsepower out of the engine. It just goes up. You just get free power on low physics pretty much. Yeah, you probably already heard me mention this, but there are two large downsides to these types of engines. One, they lock into a specific RPM, which is only a downside depending on the application. And two, they're really, really heavy. Now, these still have a better power to weight ratio some of the time than conventional engines, but because wheel friction scales directly with the contact force, you can more or less circumvent any downsides of that for a wide range. This is where I can demonstrate my car. Now that you know more or less what you're looking at here, this suddenly isn't so intimidating anymore. There's still this other flywheel. This other flywheel is just used to counteract the gyroscopic precession of the main engine. But one way we get around the locking into an RPM issue is we will use a clutch to separate them. So here I have two gas engine bearings that are facing into one another, and they're pointing opposite directions. Now the gas engine is not providing any power. I want to keep that in mind. All of the power that's in this engine is only coming from the pistons. The bearing that's here, I used to start it from my seat. Gas engines will top out at 707 RPM. Pressure engines like these will lock into 1,254. So the gas engine cannot contribute any power in the engine. And in the clutch, since the bearings are facing opposite to one another, their torque forces cancel out. And right now they're on. So they're acting sort of like an open clutch or a clutch that's slipping. You can see when I go ahead and take off the brake here, the car rolls around and the wheels are clearly rolling. You can see it's maintaining a rolling contact with the ground. Now, when I press this button, this will lock the clutches. So it's turning off the gas engine, and both gas bearings are now essentially acting as brakes. So there's a braking force in between the wheel and the engine, and that's going to allow all of the engine's torque to go directly to the wheel. And the wheels are still allowed to have some amount of slip between the left and right side, and that acts somewhat like a differential. Not really. Yeah, that curb really messed with me there. But that's the general basic principle. If you want me to go into how to set up a dedicated drivetrain, I can. I just really wanted to demonstrate what pressure engines are, how they work, and a simple-ish way to make them. I'd highly encourage you to take what I've shown you here and experiment, mess with stuff. Change the order of the parent and child between the bearings in here. There are different ways to build pressure engines that have some small nuances that are better for different things. The engine in my car has an honestly terrible power to weight ratio, and it's really complicated, but it can handle a lot of gyroscopic force. Maybe you have an application where gyroscopic force isn't an issue, so you can afford to make a more powerful engine that's, say, a bit more sensitive. Those are all options. So yeah, that's it for the pressure engines, and don't worry about that thing and that thing over there. I'll make a video on that later. But yeah, that's all.